Hello again, this is Dr. Hammond for Phys 2500 Intermediate Mechanics. This is going to be the tutorial, or the lecture for the tutorial that would be taking place on Friday, March 27th. So what I have here is some code that I'll be going over. We've gone over something similar before. This is to help you get going on the in-class assignment that I have recently posted. So this assignment shouldn't be too difficult if you've been following along. You should be able to solve for these velocities fairly, basically just using what I've already uploaded, so that you can just see how these things work. I was going to do a little bit more complicated of a question, but then I realized we needed to do second order ODEs, and we haven't done that yet. We'll be getting to that next week. So I'll be showing you some more interesting problems when we do that. So we'll be doing that on Monday, and then on Wednesday I'll get into animating your solutions so that we can see what this looks like in real time kind of thing. But for today's tutorial, what I'd like you to do is work on the assignment. So I've now posted, I'll just bring that up. Oh, I guess here it is. The assignment, the first question is basically just working on what we've already discussed, is having an object that just falls from space. So in part A, you can easily solve the analytic solution just to test your code. And then part B, we use linear resistance, and the part C, we use quadratic resistance. Parts D and E were going to be if something changes a function of height. So one would be, if gravity changes a function of height as well, and then another part would be if air resistance also changes a function of height. But since we don't know how to do second order integration, we'll be getting to that next week. But I've given you also a bonus question, and the second question is you put a charged particle in a magnetic field, and then you see that this thing goes around in a circle. So of course you use the Lorentz force. There's no electric field here, so the Lorentz force is just going to be Q, the charge of the particle, times V cross B. I give you B, it's pointing in the Z direction, it's uniform, so that's easy. Now what you just need to do is solve for V, but of course all of these are vectors, so we need to solve for Vx and we need to solve for Vy, where Vz isn't affected by the magnetic field. So you have to break this down into its vector components, of course, so you'll have f of x, and you'll have f of y, and here you'll have Vx and Vy and this cross product. So I suggest that you work that out. Show that you'll need to have two first order differential equations that you'll need to solve. Yeah, so I recommend, so if you use SI units, you'll have, the charge of the mass is 1.602 times 10 to the negative 19, and the mass of an electron, the charge of the electron is 1.602 times 10 to the negative 19 coulombs, and the mass of it is 9.11 times 10 to the negative 31 kilograms. And if you put it in some magnetic field, like 1 Tesla or something like that, these numbers are really small, and so it's sometimes kind of hard to work with. Sometimes the computer doesn't like working with such weird small numbers. So I recommend, instead of using SI units, so the standard Système International units, we use atomic units. And so atomic units, you don't have to worry if you don't know what they are. You should have seen these in Phys 1500 or in a chemistry class. But if you have not yet seen them, all you need to do is set the charge of the electron to 1 and the mass of the electron, so here mass times acceleration, of course, is just equal to 1. And then that way the computer is much happier with solving things that are like more tractable numbers. Give a magnetic field of equal to 10. That's actually an extremely weak magnetic field, but that's fine. And use an initial velocity in the x direction of 10. So of course these are atomic units. So an initial velocity of 10 isn't in meters per second, it'll actually be in terms of Bohr radii divided by the atomic unit of time, which is 152 attoseconds, if you remember how long it takes for an electron to go around a hydrogen atom. And again here, integrate from 0 to 5, where again 5 is not 5 seconds, 5 would be 5 times 152 attoseconds, if you're thinking about this in SI units. So yeah, you don't have to worry about what those units are, just kind of use more tractable units and it should be solved easily. I'll show you how I do it, but I'm using the built-in solver, and I want you to use your Runge-Kutta solver. So again, we set up our so this is for the terminal velocity part for question 1. So we have an initial velocity of 0, an initial position, I guess actually, an initial position of, here it is, an initial position of 150 kilometers, and then we have some resistance, coefficient, gravity, and the mass. And so what I do here is this is going to be for next week, using the built-in solver, we define the function, but I of course solve for velocity and position. So this is for second order differential equations, but I just want you to solve for first order differential equations. So you just have to put in V, just like what we had done on Wednesday. So you just need to do these first 2 parts. I guess there's also a part that will have linear drag as well, which should be pretty straightforward. I'll be talking about these 2 parts here for next week. And then I want you to solve for what they, solve for them, and plot them and send that to me. You can send me your code or you can send me the plots. Either way, it's fine. If you send me your code and there's a mistake, I can actually correct it and send it back to you. Whereas if you send me the plots, I won't know where you go wrong or something like that. But send that to me just to show that you've been working on this, and I'll be happy to mark it. As I say in the assignment, that this is due technically today, because it's the last day I can have anything due, and this was supposed to be for an in-class assignment. And I think that you should be able to do this very easily, but I want to make sure that you guys are working on this and understand this, so feel free to hand it in sometime next week too for full marks. But after that, I don't think I can accept it anymore. All right, so this would be how I solve it using the built-in solver. You have your Runge-Kutta routines to solve this, and so you should be able to do that as well. I can also show you for how I do my solution for for the second question. Again, I'm going to be using the built-in solver, but I want you to use Runge-Kutta. So we'll just use the atomic units. So we just have Q is equal to 1, we have our mass is equal to 1, and we have our magnetic field equal to 10. And then I say that our initial velocity in the x direction is 10, and initial velocity in the y direction is 0. And then we integrate from 0 to 5, as I say, and I have 100,000 steps. You can probably have far fewer steps, and this will still work. Now, because we have 2 directions in velocity, this is a 2-dimensional problem. They're first order differential equations, but it's in 2 dimensions. Then what we have to do is have our initial velocity, or our initial conditions in both x and y. And so then we put it into our built-in solver, and so we have Vx and Vy that we need to solve for. And so we have 2 first order differential equations, and so one of them is going to be Q divided by M times Vy times B. So if you take the cross product of V cross B, then you will get these Vx components and Vy components. And so that's the Vx component, and the Vy component is minus Q over M times Vx times B. And you just return these derivatives. And then again, I use the built-in solver, so I can just use this ODE int, and this will solve for me, and I get a 2-dimensional array. And so we just return these these arrays, and then we can plot them. So if we run this, what we get is, I still have these things labeled from before. That's funny. What we get is our Vx and our Vy, and so we initially start with some velocity, and this thing oscillates up and down, and our Vy also oscillates up and down, but you can see that they're out of phase. So instead of plotting Vx and Vy as a function of time here, we can actually plot Vx as a function of Vt, or Vt as a function of Vx, and that's what we show in the second plot. And so now we have Vy as a function of Vx, and what we get is this circle. So what's happening here is that this particle is initially coming in, and then it's going around and around in a circle. Now, of course, this just shows us a circle, but when we actually want to see, you know, what the trajectory of this motion is, we'd want to animate this, and so we'll be talking about that next week. So this is the velocities. We'd want to integrate this to get the positions, and then we'd actually want to animate this to show that this particle comes in, we all of a sudden turn on a magnetic field, and this particle loops around and around and around. So that's what we'll be working on next week. So make sure you understand how this works now, so that when we get onto these topics next week, you'll be able to do this, because part of the exam will be solving numerical integration to solve some of these problems. All right. So I guess until next week, good luck with this assignment. Feel free to send me emails to ask me any questions. Yeah, I'll see you then.